Okay, hi everyone. Today we're starting on time. Last time I had to start a little bit later, but usually I start always on time. So any questions before I start? Any concern? Please go ahead. I muted the whole class. If anyone has any questions, unmute yourself and ask. Any questions? Okay, all right, so we start. Last time we started to learn a little bit how to solve the system. And the first two sections of this book are totally devoted to learn how to solve system. So we had the system, and that's the same one I did last time, x1 minus x2 minus x3 equal to 2, and so on and so forth. And the idea is we want to solve it in the most best possible way and the fastest way. And the process we did is to actually perform operation on the system. So we end up with a system which is very easy to solve, that we were able to solve by doing what we call back substitution. So whenever the system became something simple, we started the solving. So let me remind you very quickly what was the process that we did, and then how we're going to improve on this process. So let us see what we did last time. What we did last time is the first thing we did is we tried to eliminate x1 in the second equation. So we did that by taking the first equation, multiplied it by -3. We added it to the second equation, and we left the third one not touched. So by doing this, we created a new system. The first equation remained the same. The last equation remained the same, but the second equation, we substituted it by -3 equation 1 plus equation 2. Doing so helped me to basically eliminate the x1. And then we did the same. We eliminated the 2x1. So we're using what we call elimination process. We multiplied this by 2, subtracted from here. By doing that, I eliminated x1. Now I have x1 minus x2 equal to 2, this equation and that equation. When we reach the stage, we start moving to the smaller system. And we actually use the same principle. We try to get rid of x2 in one of those equations. So the way we did it was we first flipped equation 1 and we flipped the equation, actually not equation 1, we flipped equation 2 and equation 3. And then we wanted to eliminate this x2, we multiplied it by -2, we eliminate the x2. Once we reach that, we hit a very easy system. That's the system we reach. Now when we look at the system, we actually said, you know, that's easy to reach, to solve. So x3 equal to 0, we went by doing what we call back substitution. If x3 0, it means x2 has to be 5, x1 has to be 7. And then we went back, so we got for solution 7 for x1, 5 for x2, 0 for x3, and then we went back and make sure we got the right answer by substituting them here. So that's how we solve the system, and we call this elimination process. Now what we are going to do today is actually improve on it. So we're going to start using matrices to do almost the same thing. So let us remember, to every system, we associate what we call an augmented matrix. Now what's the augmented matrix? The first row is nothing more than the equations, intuitively, without writing x1, x2, by just writing the coefficients of them. x1, -1, and the 2. 3, -1, 2, 16, 2, -1, 1, 9. So these are the coefficients and these are the augmented term. Now, what's the operation we did here? Let's a little bit think about it. To eliminate x1, I multiplied this by -3, and then I added to equation 2. But actually, what did we do? When we multiplied the equation 1 by -3, it means we took the coefficient of x1, which is 1, we multiplied it by -3, and then we added it to 3. So we really were working with the coefficient, which gave me a 0. Then I took the coefficient of x2, multiplied it by -3, which gave me the 3, and then added it to the coefficient of x2 here, which gave me the 2. So I'm really acting on the coefficients. So x1, x2, x3, I'm not really doing much for them. I did the same with x3. I multiplied x3 by -3, which gave me the 3. I added to the 2. Watch, I'm working with the coefficient, gave me the 5. I did the same here. Multiplied this by -6, added to the 16, gave me the 10. This corresponds to doing what on the augmented matrix? This corresponds to doing the following. What I did is actually, I took this first row, which corresponds for the coefficient of x1, x2, x3. I multiplied this by -3, and I added to the coefficient of x1 here. That's what I did. -3 plus 3, that gave me the 0. Minus -3, that gave me the 3, -1, which would give me the 2x2. And here, I took this one, multiplied by -3, which gave me a 3 plus, which gave me the 5. And I multiplied this constant term by -3, give me -6 plus 16 equal to 10. So instead of working on the equation, we're going to work on the augmented matrix. So what operation coincide or correspond to that? The operation correspond to that is the following. We're actually gonna replace. So what happened here is that we did not touch the first equation, because we did not touch the first row. We did not touch the last equation, we did not touch the last row, but it's the second row has been changed. So we're gonna replace the second row by. So what corresponds to this on the augmented matrix is the following operation. -3 times the first row plus the second row. So doing this operation on the equation corresponds to doing this operation on the augmented matrix. So we will write this operation as we multiply this by -3 plus R2, and this will become my new row 2. Okay, so let us now write the matrix that correspond to that. So I'm going to write it again here. So that's the augmented matrix. So the first row, we kept it the same. Now the last row, we kept it the same because we kept the equation the same. It's the second row that we changed it because we changed the second equation to eliminate x1. And this became -3 plus 3, which gave me a 0, minus -3 plus 1, which gave me the 2, and minus -3, which gave me a 3 plus 2, which gave me the 5. So now I'm acting on the rows instead of acting on the equation themselves. And then I'll have -3 times 2, which is a 6. A 6 minus 6 plus 16, this gives me a 10. So the idea is instead of working on the equation, keep writing x1, x2, x3, I really don't need to do that. I'm going to start working on the augmented matrix itself. Okay, so that's the coefficient of x1. We used it to eliminate the x1 in the second equation. Now I'm going to proceed exactly the same, but instead of acting here, I'm going to perform it on the augmented matrix. So what is the second step I'm going to perform here? If we keep in mind what we did for equation, we can do that on the matrices. That's the coefficient of x1 here. I want to eliminate the coefficient of x1 down here. So what I did, I multiplied this by -2, and I added to that. I did not touch the first, I did not touch the second row. I actually worked with the first row. So now what I'm going to do is I'm going to replace. So I'm doing that, but on the rows, not on the equation. Replace the third row by minus the first plus by -2 times the first plus the third row. That's the operation I'm gonna do on the row. Now, if I do it, I should get the system here, but we're gonna do it on the matrix instead of doing it on the equation. So I kept the first one, I did not touch it, I did not touch the second row. It's here. I want to get rid of this 2. So I do minus 2 plus 2, it's a 0. Minus minus, now it's the coefficient of x2 I'm working with. Give me a 2 minus 1, it's a 1. Minus minus 2, which give me 2 plus 1, that's a 3. Minus 2 times 2, that's minus 4. Minus 4 plus 9, give me a 5. Watch carefully. This augmented matrix is really the augmented of this system. So that's how we're going to substitute this whole picture. And then we kept going, The second thing we did, okay, we're done with the first equation, was x1. We eliminated x1 from the second and the third. Now I wanted to eliminate the x2. That was the idea. So the way we did it, we say, okay, we're gonna flip the 2 rows. So that's exactly what we did, because we flipped the equation. So now I'm gonna flip the 2 rows. Row 2 and row 3. And this corresponds to this operation. Now by doing this, I will get the following. I did not touch the first equation, but I flipped those. Just because I like 1 and 10, okay? And then what we do? We said, you know, this is the x2. I wanna eliminate this one here. So what operation do I do? The first, I don't touch it because I eliminate all the x1. I take minus 2 times the second row. I add it to the third, and the resulting thing become my new row 3. So we ended up with that. If I do this, that's what I get. 1 minus 1 minus 1, 2. This I did not really do anything. And then I will get here minus 2 times 0 and the 0, that's a 0. Minus 2 plus 2, that's a 0. My process is to eliminate the x2 from here. Minus 6 plus 5, that's give me the minus 1. And finally, minus 10 plus 10, give me the 0. So I'm doing the same thing, but instead of working on the equation, I'm working on the matrix. Already, that's really a good improvement. I don't have to write x1, x2, x3 anymore. Now, when I was working with the system, when I reached this stage, I knew that I can stop basically, and I can read the solution. Now, when I reach the matrix here, when I reach this triangular form, if you want, that's we stop and we write the system that corresponds to this augmented matrix. So if I write the system here, let's see what the system is. 2x2 plus 3x3 equal to 5 minus x3 equal to 0. At this stage, I can basically back up here and I do back substitution. Okay, so we're going to do this. We did all that because we have a lot of definition today. And all the definition I'm going to do are motivated actually by this example. So 2 things. First, we're going to define, we're going to call the operation that I performed on the matrix. We're going to give them a name and we will call them elementary row operation that I will define in a second. The second thing we will define today is the following. If I'm working with the system, I know where to stop. Whenever I have this triangular shape and I can see it, I can stop. If I'm working with the matrix, what shape should the matrix have so I can say, you know, I'm ready to solve? We will describe also the form of the matrix. Okay? So this is the motivation of every definition I'm going to talk about today. So the first definition is elementary row operation. Elementary row operation are the operation that I performed on the matrix here to be able to make it, to reduce it, quote unquote. So what are the elementary row operation? Replacement. What's the replacement? It means replace one row by the sum of itself and a constant multiple of another. This operation performed on the row was absolutely crucial. We replace a row by the sum of itself and a constant multiple of another. This operation will help me to eliminate x1s and x2s. That's called an elementary row operation. Another operation that we will do is the interchange. Interchange means just flip two rows. That's what interchange. So Ri and Rj. A third operation that we can perform called elementary row operation is the following. Multiply each entry in a row by a non-zero constant. This is also called an elementary row operation. And if I multiply the row Ri by k, we write it KRI becomes the new Ri. So these are called elementary row operations. What are those elementary row operations? What do they tell me? If you have a system, let's do it. If you have a system, you take the augmented matrix and you perform a row operation on the augmented matrix, you do not change the solution of the system. That's the benefit of the row operation. Those row operations keep the solution the same. So if I have this augmented matrix, and this system, that is augmented matrix. I perform a row operation on it. And that's the system that corresponds to the new augmented. This one and this one have the exact same solution. So performing row operation on the augmented matrix does not alter the solution. It actually simplifies it. That's very crucial. So in the scaling part, why do I say we have to multiply each entry in a row by a non-zero constant? Why did I put non-zero constant? Because what happens if I multiply a row by a zero constant? How will this affect the system? Anybody? What will happen if I multiply a row by a zero? If I multiply a row by a zero, I'll actually get rid of a row. Getting rid of a row means I'm getting rid of the equation, and that's absolute nonsense. You cannot get rid of the equation. So the row operation, exactly, we can get rid of the basic row. It means getting rid of the equation. We're not allowed to do that. So the idea of the row operation is that they will not alter the solution, but just simplify the matrix. So elementary row operation, we will be working with them. As I said, everything we do today, we're working with it to the end of the semester. When I say elementary operation, that's what we mean. Part two is row equivalent matrices. What does this mean? Suppose I have two matrices. Sorry. We say that they are row equivalent if one matrix can be transformed into the other by a sequence of elementary row operation. And we write A row equivalent to B. What does this mean? It means the following. If I take a matrix and I perform any row operation, I get another one. Those two matrices are called equivalent. That's what the equivalent means. So equivalent matrices, it means matrices that we can get from each other by a row operation. And if the two matrices are equivalent, then the system that corresponds to them have the same solution. Now we're going to go slowly into defining the shape. We will define what shape should the matrix have so that we can actually start solving. So, part two, leading entry. Suppose you have a matrix, not necessarily augmented, just any matrix. What does the leading entry in a row mean? The leading entry in a row of a matrix is the first non-zero entry in this row. When I say the leading entry in a row, I mean the first non-zero entry in this row. So let us start here. What's the leading entry in the first row? It's the first non-zero. That's the leading entry, a box. Let me take this row. What's the leading entry in this row? The leading entry is the first non-zero term. It's 2 in this scenario. Right here, the leading is 1. right here, the first non-zero term, the leading is -2. So when I say a leading term, I mean the first non-zero term in a matrix, 1, 2, 1, and -2. Now, we're going to define something called echelon form. So now I am trying to basically define a shape that I'm interested in. So we read this very carefully. Okay, now it's working. Now, suppose we have a matrix, not necessarily augmented, just any matrix. We say that this matrix is in echelon form. Echelon means like stairs. Echelon form that a lot of time I will abbreviate to EF if it has the following 3 properties. First, all non-zero rows are above any rows of all 0. Another way to write this, it means all rows of zeros are at the bottom of the matrix. That's the first condition. So if you have a matrix which says in echelon form, first, all rows of zeros are at the bottom. Second, each leading entry of a row, so we just talked about leading entry. Every leading entry is in a column to the right of the leading entry of the row above it. So a matrix in echelon form is first, all rows of 0 at the bottom. Second, every leading has to be in a column to the right of the leading entry in the row above it. Third, all entries in a column below a leading have to be a 0. Once you have a leading, everything below it's a 0. So a matrix is in echelon form. It satisfies all the 3 properties. So let us understand them. Now I'm going to take matrices, and my question is, which one is in echelon?
Professor?
Yes.
Could I see the third one again? I didn't get to write it down.
Sure. All entries, verbatim from the book, that's why I'm comfortable. All entries in a column below a leading are zeros. I want you all to look at them because this is to have to be totally under control.
I got it, thank you.
Okay, sure. Now, let us understand it. I have a bunch of matrices, and forget about the second word for now. We'll introduce in a second. So my question now is, decide which matrix is in echelon form. For each matrix, we have to decide which one is in echelon form. All right. And you know, this is 1, 2, 3, 1, all rows of 0 at the bottom. 2, it means every leading in a row is to the right of the leading in the row above it. The last is all entries in a column below a leading has to be 0. So each one of them, I want to tell me, is it in echelon form, yes or no? The first one, is it in echelon form, yes or not, quickly?
No.
No, because? All the rows of zeros has to be at the bottom. This condition is not satisfied. So condition 1, not satisfied. Okay, that's it. We move on. That's an easy case. 2, is it in echelon form? Now, the first thing I advise you to do, and you guys will do it, is that whenever you have a matrix and they're asking you those questions, I want you to, in this beginning, look at the leading. That's the leading, and that's the leading. Now we can answer this question. Is this matrix in echelon form, yes or not?
No.
No, it doesn't satisfy 2 because, sorry, actually it doesn't satisfy 2 and 3. In the echelon, all the entries below the leading has to be zeros. After question, that's a leading. Below it is not a 0, so definitely not in echelon form. Okay, now we move on. This matrix, that's a leading, that's a leading, that's a leading, and that's a leading. Is this in echelon 4? Yes or not? Quickly.
No.
No, because.
No,
No, because quickly.
because it doesn't follow rule number 3.
It doesn't follow 3. That's a leading. Everything below it has to be 0. So again, a no. So a lot of example of no. Of course, you're going to ask me if there a yes. Of course. Leading, leading. Is this in echelon 4? All the rows, there is no rows of zeros. Every leading is to the right of the leading before it. Everything below the leading is 0. That's in echelon 4. That's the 4 that I want. The last one is, my memory is fairly similar to that. That's again in echelon 4. Okay, so now we understand echelon 4. There is another type of matrices, reduced echelon 4. Suppose you have a matrix which is already in echelon 4. It's already in echelon form. It means one of those forms that we have. We say that this matrix is in reduced echelon form, and reduced echelon form, that's how I usually write it, if it also satisfies the following. Don't worry about that. If it also satisfies the following: the leading entry in each non-zero row is 1. So suppose you have a matrix in echelon form. We say it is in reduced echelon form if satisfy every leading is 1. Every leading is the only non-zero entry in its column. So reduced echelon form have to satisfy something else. The leading has to be 1. Every leading has to be the only non-zero in its column. Now let's go back and see which one is in echelon, in reduced echelon form. First, to be in reduced echelon, it already has to be in echelon form. So this goes, this goes, this goes. Now this is in echelon form. Is this in reduced echelon form? Yes or no? These are the conditions. Every leading is 1. Every leading is the only non-zero in its column. So is this in reduced echelon form?
No.
No.
Definitely not. Also not reduced echelon form. Now, is this in reduced echelon form? It's an echelon form already. All the leadings are 1, satisfied. And the last one is what? Every leading should be the only non-zero in its column. Crucial. What was the second condition for reduced echelon form? It's a very important one. I read it. Each leading is the only non-zero entry in its column. So once you have a leading, that's the only non-zero entry. So in this scenario, that's the leading. That's the only non-zero here. That's a leading. It's the only non-zero. That's the leading, only non-zero. That's reduced echelon form. Okay? Let us say I have the following. So if I take the following matrix, a slight variation of that. 1, 0, 3, 0, 0, 1, 3, 1, 0, 0, 0, 1. Is this in reduced echelon form?
No.
No, because the leading are 1. Every leading is to the right of the one before it. Every terms below the leading is 0, so it is in echelon form. But the reduced echelon form requires leading to be 1. I took care of that. But they require that every leading is the only non-zero in its column. And this one had that. So that's definitely not reduced echelon form. Okay, so that's really the difference between them. And okay, now what we're going to talk about now is the following. Any matrix, regardless how complicated it is, any matrix, we can perform row operation on it, elementary row operation. So we can transform it into a matrix in echelon form. Also, any matrix, regardless how complicated, we can perform row operation on it, so we can transform it into a reduced echelon form. So, and that's the theorem that we're gonna learn how to do it today. So let me read it one more time. Any matrix, doesn't have to be augmented, just any matrix, can be row reduced. What does the word row reduced mean? It means transformed by elementary row operation. So we can perform operation on it. So it can be transformed into a matrix in echelon form. So it means every matrix is equivalent to a matrix in echelon form. So we can work with it till it become echelon form. Also, something more, every matrix can be row reduced. It means you can perform row operation on it to, I will talk about that later on, to one matrix in reduced echelon form. So we can take a matrix, make operation on it, so the last matrix we get is in echelon form or in reduced echelon form. The theorem tells me the reduced echelon, the echelon form is not unique. It means you can have different ones, but the reduced echelon form is a unique. It means you can have only one. And I will talk about that once we start learning how to do this. Okay, so now what we're going to do is what we call the reduction algorithm. The reduction algorithm is the algorithm we use to, starting from any matrix, what's the fastest way to perform row operation so that the result is in echelon form. So that's what's going to be our next step. And this one we will work it out in class. Row reduction algorithm for any matrix, not necessarily augmented. The question is, we have a matrix A. My question is, reduce the matrix below to echelon form. What does this mean? It means transform it by row operation to a matrix in echelon form. Means I want to take this matrix, use operation so that the resulting one is in echelon form. And that's the algorithm. And that's the algorithm that you guys will have to follow. Let's see how it works. All right. How we reduce the matrix. The first step is the following. Remember, the way we're gonna do was motivated by operating on a system. That's really where the idea comes from. So this should not be very hard. The first step we do is the following. This is a matrix. The first step is we create a leading in this spot right there. So that's the first step we're going to do. So we use the elementary row operation, which are replacement, exchange, and scale to create a non-zero term or a leading in the spot right there. Very important. That's, think about this, the coefficient of x1. I want to create a coefficient here. All right, so that's the first step. So create, I write in red, create a leading entry here using the operation. So how can I create a leading entry? Which operation I can use?
The first one?
Which is?
The row replacement?
No.
Oh, like switching them up?
Switch. Switch.
Yeah.
Switch.
Yeah. Interchange.
Interchange. Right. So let us do that. Now, which one you switch? The only one I don't want is this one because this is it too. I don't want it two in here, and you will know what is it. I can switch the first two rows. I can touch row 1 and row 3, but I don't want to work with 2. Just keep 2 here. So the first operation, I want to create a leading entry here. So to create a leading entry here, we're going to do R1, interchange, and R2. And that's the algorithm we will all follow. If there is no leading. If there is leading, I'm done. I don't have to do anything. I have to do other things. So this is mean, that's the equivalent. So I'm going to create another matrix. So this is the matrix. Now I will do it. 1, 2, 3, 16, 0, 1, 4, 18, So if I do any computational mistake at this stage, it will be up to you. You guys will have to correct me. 2, 1, minus 6, 2. That's the first step in the algorithm. Now I created my leading right there. As you realize, I always put it in, in a box. It's crucial. That's going to be what leading me. The second step is I will use the leading, this one, to make everything below it into a 0. So I will use the elementary row operation basically to make the one below it a 0. Let's think of eliminating x1 in your head and creating a 0 right there. So what elementary row operation I'm going to do to create a 0 here? Go ahead.
Scaling?
Why scaling? I want to create a 0 in here. So we're going to use the leading. That's really my approach. Use the leading to create zeros under it.
Oh, wait.
That's really my strategy. So which is the best operation? Anybody? Replacement. What do I mean by replacement? I'm going to multiply the first row by -1, add it to the third row. By doing this, I'm going to create a 0 in here. And then the result will be my new row 3. So we're going to do replacement. Okay, I'm going to write it in words and symbolically. We're going to replace the third row by minus the first row plus the third row. Okay, symbolically, minus my apology. Minus R1 plus R3 will become the new R3. So I pick up another piece of paper and I will do this operation, so all of you can see it clearly. So now what I'm going to do, 1, 2, 3, 16. I'm not touching the second row because I have a 0 in here. I'm not touching the third row, the last row, sorry. It's this row that I'm going to replace. I'm going to replace it by what? By minus the first plus that. -1 plus 1. That's a 0. That's how I'm creating my zeros. -2 plus 1. -1. -3 -1. Minus that. -16 -2 -18. So first we create a leading in the spot. Now I'm going to use that leading, so the top, to create 0 under it. So now I created my first 0, I had it. I created my second 0. Now I want to make this into a 0. Which operation I need to perform to make this into a 0? Replacement, scaling, and this, or interchanging. What shall I do to create a 0 in this spot? Now we need to create a 0. Quickly?
That would be the scaling, I think.
No.
No, brain, sorry.
No. What do you think I'm going to do? How can I create a 2 here?
Oh, replacement.
Isn't the third term in the third row a -4? This one? -3, -1, absolutely. Thank you very much, Marquita. And somebody else. Very good. Thank you. All right, what shall I do now? Quickly. How can I create a 0 in here? I'm going to use the leading, multiply this by -2, and add it to this one. So again, I'm going to use replacement. I'm going to replace the fourth row by minus 2 times the first plus R4. So symbolically, I'm going to take the first row multiplied by -2, add it to the fourth row, and the result will be my new row 4. Okay. So let's see what we get. And here equivalent, it means those matrices are obtained from each other by elementary row operation. So let's say A1, A2, A3, 16, 0, sorry, 1, 4, 18, 0, I did not touch those, minus 18. Now, what did I do? I want to create a 0 here by elementary operation. Minus 2 plus 2. That's how I am getting my 0. Then, minus 2, which is minus 4. Minus 4 plus 1. Give me a minus 3. Minus 2, which give me a minus 6. And minus 6, that's a minus a 12. And this I have to multiply by minus 2. Let's give me a minus 32. Minus 32 plus 2, which is minus a 30. Okay, so let's repeat the algorithm. Step 1, so my goal is to perform operation till the end become an echelon form, but we have to do it algorithmically. I create, so step 1, I create a leading in the spot. I created it. Step 2, going from top to bottom, I'm going to use this leading to create a 0 in here. To do that, I need the replacement minus the first row plus the second. I create a 0, and then I use this to create a leading right there. And to do that, I did minus 2 the first row plus that row, and this will create my 0. Once I do that, so in this process, as for if, imagine, this is not an augmented, but imagine this is an augmented. What I am actually doing of a system, I am eliminating the coefficient of x1. That's really intuitively what I am doing. But what we're doing now work for any matrix. So that's my leading. Now, once I make everything below my leading into a 0, I move to the other leading. I go to my second row. So I move to the right and below to the other, and I try to create a leading in the spot. So right now, I forget about, not forget, but I ignore this a little bit, ignore this, and now I start thinking, repeating the process on this smaller matrix. That's how we're going to do it right now. So we move to the right, and we move to the bottom right there. And I need to create a leading in this spot, but I have one. Okay, and now, I don't think minus 40, I think it's minus 30. How did I get here? Minus 2 times 16. Yes, I'm right. Thank you, Philip. Anyway, so I'm going to create a leading here, but I already have a leading. And now what I'm going to do, I'm going to use this leading to create a 0 in here and a 0 in here. That's how my algorithm. So now I'm basically focusing on what I can call the submatrix. And I'm going to repeat the process on this little matrix down here. So how can I create a leading in this spot? Sorry, how can I create a 0 in this spot? Quickly, I want answers right now. I want to use this leading to make everything below it into a 0. Everything below it into a 0. How can I make this one into a 0? Which operation shall I use?
Replacement.
Again, what is it? Say it in word. What shall I do?
Multiply.
Add it as is.
R1
just
plus
adding them.
R2.
1 minus 1 will give me a 0. That's really what I have to do. Okay, so to create a 0 in this one, in this row, so we have to nothing more than replace R3 by the sum of R2 and R3. It means I'm going to take R2, add it to R3, and this will become my new R3. Because 1 minus 1 will give me a 0. That's the operation I'm going to do. So let's do that. One, 2, 3, 16. Very good. 0, 1, 4, 18. I did not touch the last row. It's this one that I am changing. How am I changing? What I'm doing is I'm taking the second row and adding it to the third. 0 plus 0, 0. Everything I do should never give me a non-zero number. If I do any operations that create a non-zero number here, it means I'm doing something wrong, because once I guarantee everything below the leading are 0, I want them to stay like this. Now, 1 minus 1 is a 0. 4 minus 4 is a 0. 18 minus 18 is a 0. Okay, I keep track with my leading. They're crucial. They're called leading for a reason. Now, what am I going to do? Everything below the leading, I wanted to make it into a 0. Now, I know I see this row of 0. Don't worry about it. I actually see it. I want to create a 0 right here. So once I create a leading, I want everything below it is 0. I created a leading. I want everything below it is 0. What shall I do? Again, another replacement. I'm going to multiply this row by 3 and add it to this one. Then I create a 0 in here. So we're going to take the second row, multiply it by plus 3, add it to the last row, and then the result will become my new R4. So the process is create a leading, everything below it, make it into 0 by using row operation. So this is going to give me the following. I did not touch the first one. I did not touch the second one. I did not touch this one. The only one I'm altering is the last one. So let's see how we're going to do it. I multiplied this by 3 and added. 3 times 0, 0. I'm not affecting anything. 3 minus 3. That's a 0. 3 times 4, 12. Minus 12. That's a 0. 3 times 18. 3 times 18 is 54, right? Minus 30. That will give me 24. So now, that's a leading. That's a leading. And, okay, that's a leading. Here, there is no leading here. I will stop performing when my matrix is in echelon form. All right, that's really my goal. Is my matrix in echelon form, or I need more operation?
I'll just switch the third and fourth row.
I have to switch because this is not in echelon form. So now I still have to switch row 3 and row 4. So I need another piece of paper and I will switch them here. So I will get the following. I need pencil because I do stupid mistake with that. Very good. 0, 1, 4, 18, 0, 0, 0, 24, 0, 0, 0. Okay, and the leading are here, here, and this is a leading. Now, is this in echelon form?
Yeah.
Yes, so it is in echelon form. And then we can, if you want, we can stop here. That's my reduction. Okay, so that's how it reduced the matrix to an echelon form. So let us a little bit review the algorithm. How was the algorithm done to reduce a matrix? So our algorithm is like that. That's the one, as I said, you will have to use. Step number 1, create a leading in the stop entry. Once I create it, I use operation. Well, a lot of time they're going to be replacement, most of the time, to create a zero below the leading. So I start from the top, create a leading here, I make everything under it into a zero. So I did that, I reached the stage. Once I am done, I move to the right and below, right, below. And I create a leading in this spot right there. And then I repeat the process. I use replacement to make everything below it into a zero. And that's exactly what I did. So we hit right there. And now the idea is basically to move to the right again and create a leading. But in this case, there is no way I can create a leading because what's below it is zero. So I had to move here again and below. And actually try to create a leading in here. To create a leading here, I had to switch to 24 out of the problem. So we go leading, the top, everything zero, right, down, create a leading, everything zero, and that's the algorithm. Then we move right, bottom, create a leading if possible, and then till we end with the matrix. Okay, so that's the algorithm that we are going to follow. Now, to comments. Comment number one. Let us say a student does the following. A student doesn't like the 24, and he does the following operation. The scaling operations that one of your classmates want me to do all the time. So suppose I scale the third row. So I divide by 24 and make this into row 3. Is this an acceptable row operation? Is this one of the elementary row operation? And the answer is yes, because multiplying, and if you think of it as an equation, multiplying an equation by a non-zero constant doesn't really change the equation. But in this case, this does not have to be the augmented method of a system. So this is an acceptable row operation. So you can either stop here or you can go one more step. And you will, of course, eventually understand why sometimes we like nice numbers. 1, 0, 0, 0, 0. So my leading are exactly here. They didn't change, but this term is easier than that. This brings me back to a comment I did at some point, and I told you that I will talk about it. When we use the algorithm to reduce a matrix to this shape, all of us should have the same position of the leading. What do I mean the same position? All of us should have a leading in this exact spot of the matrix, first row, first column. All of us should have a leading in this spot, second row, second column. All of us should have a leading in this spot, fourth row, third row, fourth column. Sometimes, so the position of the leading will be the same across the whole class. But if we are in echelon form, some students may decide to scale, which is acceptable. Some students decide to stop here, which is acceptable. So we will not have exactly the same, but the position of the leading within the matrix will be the same. So that's the echelon form, and that's the algorithm. So the algorithm.
Can I ask a question?
Yes, of course you can.
So the third row, you have all the coefficients being 0.
Yes.
Assuming that this matrix represents an equation, if we put this back into a linear equation, we get an equation that says 0 is equal to 24, or 0 is equal to 1. How is that acceptable?
This means that this equation has no solution or whatsoever. It means the system that corresponds to this equation is an inconsistent system.
But the operations are still fair game?
Absolutely. Absolutely.
Right.
Absolutely.
Thank you.
Replacement, and that's going to be crucial. I mean, that's why if I have time, I'm going to start with that idea, because the row operation do not change the solution of the system. They keep them exactly the same. Not at all. Because multiplying an equation, switching equation doesn't change the solution. Multiplying by a non-zero does not change the solution. Even multiplying an equation by a constant and adding it to another will not change the solution. And that's crucial. That's why we are allowed to do those operations. Am I with you?
Yes, thank you.
Okay. So, and that's going to be crucial. Anyway, now, if a matrix in echelon form, the second question would be, how can I put it in reduced echelon form? You know, we have two forms. So the second part is how to go from echelon to reduced echelon. What's the algorithm? Because that's what we will be doing with the matrix. Eventually, what we will be doing is once we start with this system, what we're going to do is reduce, take the augmented matrix and actually reduce it to its echelon form and then solve. Or sometimes to its reduced echelon form. Today, I'm going to emphasize the algorithm, and next time, I'll emphasize the solution. So the third question is how to go from echelon form to reduced echelon form. It means if our matrix is in echelon form, I don't understand the chat here. Anybody has anything? I don't understand. Sometimes, yes, I'm having it. I don't understand what you guys. Are you having problem with fine on my end? All right, I have to keep going. So now my question is the following. Sorry. All right. So if a matrix is in echelon form, how do I go to the reduced echelon form? And this is the second part of the algorithm. So suppose I have a matrix, it's the same matrix A, I'm not gonna change it. And the question is, reduce the matrix to reduced echelon form. So that's my matrix. And my question is, reduce the matrix to reduced echelon form. How do we do that? It means I want to keep performing row operations and the end result is in the reduced echelon form. The first step is you start with the matrix and you put it in echelon form, the way we did a minute ago. Once it is in echelon form, we're going to perform more operation so we can put it in reduced echelon form. So the question is how we're going to go from here all the way to the reduced one. Remember the difference between them. The difference is in the reduced echelon form, all the leading are 1. By me dividing by 24, I created ones. And the second condition is that every leading is the only non-zero in its column. And that's the one I'm going to go after it using operation. So let's see how the algorithm works in a case like that. So I have my matrix A, the original one I started with. I perform operation to make it into echelon form. So we did a lot of operations and that's where we are right here. And pencil is much better, so I can erase 0, 0, 0, 1, 0, 0, 0, 0. Now from here, I need to go to the reduced and let's see what's the fastest algorithm. All the time, leading plays such an important role that we always emphasize. The algorithm go like that. I will start with the bottom leading. I start here. Okay, the bottom leading. So the leading to the far right. And I will use this leading to create a 0 in here and a 0 in here. That's how the algorithm would go. So we're going to start with the leading at the farthest right, which is at the bottom here, and create a 0 here and a 0 here, because I want it to be the only non-zero. And we're going to use replacement or switching or elementary row operation. So what do you want me to do? To create a 0 in here. I'm going to take this row, multiply it by minus 18, and add it to the one above it. By doing this, I create a 0 in here. So let me write this down. We're going to replace the second row by minus 18 row 3 plus row 2. And by doing this, this will become a 0 here. So let us do that. 0, 0, 0. 0, 0, 0. So I always start from echelon to the reduced echelon. I always start with the leading at the bottom or the far right one. And I use it to create 0 above it. So I'm not touching the first row now. It's the second that I'm changing. So I multiply this by minus 18, added, I'm not changing anything. That's a 0 here. Multiply by minus 18 added, I'm not changing anything. 0, minus 18 added, I'm not changing any, sorry. I'm not changing anything. Now, minus 18 plus 18, this gives me 0. Okay. Now, I want to go to the reduced echelon form. I need to create a 0 in here. I will do the same. I use this leading, which is a 1. That's why 1 is nice. It doesn't have to be 1, but we were lucky in this problem. And I use it to create a 0 right at this spot. So again, I'm going to do another replacement. So I'm going to replace, I'm going to take the third row, times it by 16, minus 16, add it to the first, and this is going to be my new first row. So let us see what we do. I did not touch the last row. I did not touch this one. And this one is, I didn't touch it. So this is my leading. I keep my eye on it. This is my leading, crucial. And now let's see what we did. Minus 16 times 0, it's a 0 plus 1, it's a 1. And now minus, sorry, I'm here. Minus 16 times 0 is a 1. Minus 16 times 0 is a 0. So I'm not changing that. That's why the algorithm is good. That not changing that. Minus 16 plus 16, it is a 0. So I start with the far right. I use it to create 0 above it. Once I finish, then I move to the left. So I'm using, the way we're moving is bottom to top, right to left, like opposite to what we're moving before. So now I move to the other leading, to this one. And I use it to create a 0 right there. To be able to create a 0, again, I have to multiply this row by -2. I add it to the first. And this will become the new row 1. So let's see what operation we get. 0, 0, 0, 0. And 0, 0, 0, 1. 0, 1, 4, 0. And now I'm working. Minus 2 times 0, it's a 0 plus 1. I'm not changing that. Minus 2 plus 2, that's a 0. And then minus 2 times 4, that's a minus 8. Minus 8 plus 3, that's a minus 5. Minus 2 times 0, it is a 0. And now this matrix is in reduced echelon form, and we're done. Now, the reduced echelon form is unique. It means we all, regardless how we do our operation, because sometimes students play around with their operation, we all should get the exact same matrix. There is no difference between us. In the echelon form, there may be some variation, but the position of the leading are the same across the board. In the reduced echelon form, we all get the exact same matrix. So let us summarize how the algorithm. To go from echelon, the matrix to the echelon. We start from the top, create leading, make everything under 0, then we move to the right, create a leading, everything 0, and then we keep going. That's from the matrix to the echelon. From the echelon form to the reduced echelon form, the fastest way to be able to do that is start with the far right leading. Use it to create 0 above it. Once we did that, then we move to the left to the other leading, bottom leading. And we repeat the process. We use it to create a 0 and off it. Okay. Now a definition. As I said, that it's a theorem that we can prove that regardless how we do the operation, even though sometimes students have a variation on what I do, we all have the same position of the leading. It means we all have a pivot, sorry, not a pivot. We all have a leading here, and a leading here. The same position. Nobody will have a leading right there or here. We all should have the same position. And this will motivate the following definition. The pivot column that the book talks a lot about. What's the pivot column of the matrix? The pivot column of a matrix A, so that's my matrix, that's the one I've been working with, are the columns of A that correspond to the column with leading entry in the echelon form. So that's my matrix A. What are the pivot columns? They are the columns of A, but which column? That correspond to the column with leading in the echelon form. So to know what the pivot column are, I have to find the echelon form. So we did that. We did the echelon form. It doesn't have to be the reduced, but we did it. And what are the leading? So let me write one version. So that was my echelon form, the one we all worked on it. 0, 0, 0, 1, 0, 0, 0, 0. So that was my echelon form. And these are the leading. 1, 1, 1. So what are the pivot columns? The pivot columns are the columns in here that correspond to the column with leading entry in the echelon form. So the columns would be the first column, correspond to this leading. So that's one. The other one would be the second column. That's what we mean by pivot column. And the last column will be the third one. Okay, so it will be, sometimes we can write them this way, 1, 2, 1, 1. And the last one. This is what we mean by pivot column. So those are those columns, the columns that correspond to the leading in the echelon form. So to find the pivot column, I have to find the echelon form. There is no way out. If I look at this matrix, I have no idea what the pivot column are. And the book talked about pivot position. The pivot position in A are the position that correspond to the leading. So 0 will be called, this is a pivot position, and 2 a pivot position, and this here. Those are what we call the pivot position. They are the position in the matrix that correspond to the leading in the echelon form. Before I move on, I will ask you simple questions just to make sure a little bit we're following the algorithm. So my question is the following. Suppose this is a matrix. My question is, what is the next operation you will do based on what we learned today to reduce to echelon form? Suppose I want you have this matrix and you guys are gonna reduce it to echelon form. What would be your next operation?
I would switch the second and the third row.
Switch the second and the third. Do you agree with him?
Yes.
Yes,
Yes.
because the minute I have a matrix, that's the way, that's really here, my leading. And everything below it is 0. So I'm safe here. So if I'm doing my echelon form, I need to go here and create a leading. I don't have one. I have to create one. How can I create it? Is by switching. So you're absolutely correct. We're going to switch R2 and R3. Okay, so it's going to give me a 1, minus 1, 0, 2, 0, 1, 3, 4, and I'm done. 0, 0, 1, 3, and 0, 1, 2, 3. So that should be the next operation. All right, let me push you one more. What would you guys do after that quickly? So
Switch R3 and R4.
what?
Switch.
I think it'd be replacement.
It will be replacement. Because what do you want to do at this stage? You want to make everything below 1 a what?
Zero.
Into a 0, exactly. So now it's replacement. What's replacement? Going to multiply this by
-1,
and finish my
Plus.
sentence and add it to this one.
R4, yeah.
Okay, to R4. You multiply the second row by -1, add it to R4, you create a 0 in here. And then you proceed. All right. Now I have this one. This is a matrix. And my question is the same. What is the next operation to reduce to echelon 4? Now me being me, I always start here. And everything below it is 0. I don't know.
You could reduce row 2 scalar.
Okay, we can reduce it. That's a good idea. So I'm going to reduce it. So you want me to do what?
Divide row 2 by 2.
Yeah, so this is my leading key. Let's not get that going. And you're absolutely correct. And I want you to justify why you want me to do that.
So that our leading becomes a 1.
They don't usually have to be 1, but they will become, what's a better way? They don't have to be 1, but they will be easier in this case to work with. Okay. That's good. What will you do after this? What will you do after that?
Work to reduce through get to make row 3 to get rid of the root 2.
Very good. You want to get rid of the root 2. What shall we do?
Square the last row, the third one.
You cannot do that.
Yeah.
Because squaring a matrix is not an elementary row operation. Did I ever tell you that you can? Is squaring part of the elementary row operation? Which elementary row operation you should do? Philip, you're raising your hands, right?
You would add row 1 and row 3.
Okay. Is this correct? I want you all to listen very carefully. There is a reason I put those nasty numbers. So one of your classmates told me the following. I'll write it. And it's still there. And I want you to comment carefully. Your classmate told me you take the first row. Correct me, Philip, if I am wrong.
Yeah, that is what I said.
Very good. And let's see what we get. 1, 3, 0. He doesn't want to touch the first row. And then he told me add them. 1 plus 0, 1.
Oh.
0.
Okay.
Are you with me?
Yeah.
3, 5. Is this a correct row operation?
No.
Absolutely not. And you have to be very careful with that. Absolutely not. Because you're in doing what I have. I have the 1, I have the 0 under it. And that's the way I want. I don't want to touch those anymore. So touching the first row and adding to this will totally undo the operation. Now you have to go backward. So you make a problem into a much harder problem, not an easier problem. So what am I telling you? Once you have a leading, you create a 0 in here, you basically, especially you're going to the echelon 4, you forget about this. and you start working with that piece down here. Anything else will undo the 0 that you have right there. Is that very clear?
Yeah.
It has to be crystal clear because that's a typical mistake that the student, you know, at the beginning will do. All right, now, I'm still having difficulties here. How can I create a 0 in here using a simple row operation?
Multiplying row 2 by negative square root 2.
As simple as that. Don't be afraid. Square root of 2 is a number. So the best possible situation is exactly what we said. That's a 1. So I'm going to take the second row, multiply it by minus the square root of 2. It's a number. Add it to the third row, and this would be my new row 3. So I will not touch the first row. If I touch the first row, especially that I'm going to the echelon form, I will alter the 0. I don't want to touch the 0. And now, this times there's going to be a 0, minus square root of 2 plus square root of 2, that's a 0. And then I will have 1 minus the square root of 2. I know it's a nasty number, but it's correct. And then I will have minus 2 square root of 2 plus 2. That's the operation I will do. Okay, my last question before we go is this. To go to the reduced echelon form, first you go to the echelon form. Once you go to the echelon form, that should be the first step, and then from it you go to the reduce. So now my question to you is, what's the next operation from the echelon form to the reduced echelon form? I want you to remember the algorithm so you can do it yourself. Always you start, it's an echelon form, so I know where my leadings are. So what would be the next operation from echelon to reduce? Back to you, because we have to stop. Okay, anybody? What would we like to do now? Replace row 1 and row 2. Okay, I will do what you guys tell me and you comment. Replace row 1 and row 2. So replace row 1 and row 2. So you're not touching that. You're doing this, and you're doing that. Is this correct? Is this correct?
No, that wouldn't be.
Absolutely not. Absolutely not. Because then you're undoing the echelon form. You're again undoing something. You know, to get that's so the leading are here, the leading are here. We have a mess in our hand now. Okay, doing this will undo the echelon form. You're not supposed to undo it. So what shall we do? The leadings are 1. I don't have an issue with that. So what is the reduced echelon form? What should I do?
Start at the bottom right and try to reduce rows 1 and 2 by multiplying R3 by -1 and adding it to row 1, and by -4 and adding it to row 2.
Exactly. I start with the rightmost one or the bottom one, and I'll use it to create a 0 in here. So I multiply the fourth row, the third row by -4, add it to the second. So I need, and then this would be my new second row. By doing this, because remember, this is already in echelon form. So this is being taken care of. Now I'm going to the reduce. It means I want to make this into a 0 and this into a 0. So now 0, 0, 1, 4. 0, 1, minus 4 times R3, that's a 0, and that's a 1, I did not touch it, minus 4 plus 4, that's a 0, and then minus 4 times 4, that's minus 16, minus 16 plus 2, minus 16 plus 2, that's give me a minus 14. That's the correct operation. 1, 2, 1, minus 1. And then we have to quit, but then as your classmate said, after that, you have to create a 0 in here by using this leading. So you take minus R3 plus R1, and that would be your new R1. By doing that, you will actually do the following. You make a 0 in the first one. So 0, 0, 1, 4, 0, 1, 0, minus 14. And then that's a 1. I'm multiplying this. It doesn't matter. We haven't changed it. I'm multiplying this minus 1 plus 1. That's a 0. And then minus 4, that would give me a minus 5. And now I guarantee my 1 here, my 1, my 1. And what's above it is 0. Okay, what's the last operation before we leave? I'm 5 minutes late. Quickly, each one of you.
Multiply row 2 by negative 2 and add to row 1
Exactly.
to replace
And
row
then,
1.
exactly, and then we're done. So that's the algorithm. So that's minus 2 R2 plus R1, and this will become my new R1. And then we get to our reduced echelon form. All right, so please make sure you practice those problems for Monday, or you will forget everything we said today. All right, the homework will be on Blackboard. Next Wednesday will be your first quiz. Okay, have a great weekend. Any question before I quit?
Excuse me.
Yes.
May I
Class is done. Everybody who wants to leave, feel free to leave. Go ahead.
May I see the rules for echelon form again, please?
Absolutely. You want the echelon or the reduced one?
Regular echelon, please.
Okay. I have to look for it. I didn't throw it away. Can you be patient a little bit?
Okay.
Yeah. Oh, here it is.
Okay. So let me jot this down really quick, please.
Sure. I have time. No rush.